Hi everyone, this is April 21st, 2021. It is week 4 of Drexel spring term, so this is our 4th general body meeting for Drexel AI. This past week, we had a we had a supposed conference deadline on a Sunday that was then moved after we submitted the paper to May 10th. So that gives us about 20 days to figure out what more we want to add to this. And I'll start by sharing my screen to the archive post. I actually submitted this the night that we submitted to the conference. So thank you to everyone who contributed. And then it's up. The PDF is here. And we're at the 4-page maximum. And this was with a very small data set, which is why we think we're going to adapt it. You see for our main results right here, we have just less than 20 epochs of training, trying to show that the generator and discriminated losses both converge. This was on a set of only 10 proteins because we were crunching on time. But since then, I think Asamu's ran the 1,000, modified some parameters.
It'll be 502 proteins.
Okay. And just so you know, I do have 10,000 protein IDs that I can transfer.
No need.
It's no need. Okay. I know you said you were going to be done for the week, but
yeah.
I don't know too much about. I know Yit does and Jeff does as well about optimizing these architectures, because what were some of the problems that you noticed when you were training it?
Oh, okay. So for the new one, like you can learn a lot from looking at these curves. So where did I put the curves? I forgot. Protein nets.
You want to share your screen?
Yeah, for sure.
Okay.
So for the original one, with the original architecture, we have somewhere here, we have this curve. So basically, this is a generator which generates images. This is a discriminator. So problem here is like basically like the discriminator fits like within the first 10 epochs or so, and it's already fully trained. But the generator, it keeps kind of like, I think the model this time was it like had 46 million parameters or something.
Okay.
So it's struggling to learn basic concepts. So that's why it's kind of going up and down. Yeah, it's slightly lower, but like, and the training time was insane.
So you tried it for what, 99 or so?
Oh, this was like with 502 proteins.
I mean, how many epochs?
Oh, this, yeah, 100 epochs.
Do you think if you left it for a while, it would converge? Because you can kind of see that the peaks are getting smaller.
Maybe, but like
maybe that would take too long.
I don't wanna kind of like let my computer run for 24 hours and not be able to work.
How long did it take to get these results?
This like 3 hours or so.
Really?
Okay.
Wow.
Yeah, and for this one, this is a modified architecture, and it has like, I don't know, it went from like 45 million params to 858,000, which is quite similar to the amount of parameters for the discriminator. Actually, the discriminator is just this 200,000.
Okay.
Anyway, for this time, yeah, it's either about 2 problems. So it's either the generator is underfitting, which basically means that this model is too basic to fit to the data, or the discriminator is converging too fast.
Okay.
So for the problem of the discriminator converging too fast, I remember in the original architecture, there was like there was this plus noise here. So I'm thinking about reintroducing this, and maybe
Okay.
then the discriminator will take longer to
Yeah.
converge, and I don't know.
So what the loss we're using for the discriminator is cross entropy, right?
Yeah,
What's the loss we're using for the generator?
I think that's cross entropy too.
Isn't cross entropy for categorical data though?
Okay, so
I think the loss should be, well, how are we gonna, how are we gonna, define the loss?
currently it's getting like misleading labels. So these are raw real images. Yeah, honestly, I forgot, but it's cross entropy.
Okay. Well, how does that make any sense? Because the generator, or is this model working off of one loss function? It's working off of one loss function.
Oh, so basically,
yeah.
you have the generator, right?
Yeah.
It generates something, and then the discriminator.
Yeah, that was my bad.
Yeah.
I thought there were two loss functions. Never mind.
Well, there's like the discriminator loss and generator loss, and they are each applied to the discriminator and generator.
Okay.
And basically, I'll just explain this quickly because I just figured it out. So basically, the generator generates something. You know, the discriminator needs to say is like for all the generated images, it must say like it's fake. So the prediction should return all zeros or something. So it's just comparing that loss.
Okay. So the paper that Jeff sent us originally, they used protein contact maps or distance matrices of proteins, and it worked well. I think it worked well. It worked well enough for them to publish a paper. That's all we care about. I'm joking. So is there a way that you can kind of integrate this representation? Because our idea was to replace the contact map representation with the 3D structure and then use convolution to kind of replace, because like the contact map has distances of each atom, at least how far they are, but the grid structure, that still has the positional relationship between all the atoms if you use a convolution net like we did in the GAN, but it didn't work as well. It might be because the model architecture is poor, but we might want to go back into that original paper and see what model architecture they did, because we're both encoding positional relationships still, right?
They're using convolution too?
Yes.
Oh, okay. Then maybe we can copy their architecture.
I think that would be a good idea. But we're using a different representation.
I have kind of like the basic idea, you know, like how much to scale up.
Yeah, that makes sense. Cool.
Oh, I forgot to mention. So one reason I think it performed poorly too was, oh, not here. Okay, so we originally got like data within this range, but I modified the generator to generate these kind of sizes. But basically, because it's easier to do convolution that way. Yeah. But for that, I need to pad the data. So
I don't think padding the data would do anything. You're just adding zeros around it. That'd be just selecting a larger rectangular prism around all the points.
Maybe.
Yeah.
I don't know, but like it might be a card. You never know.
Yeah. Hey Jeff.
Hello.
We were just talking about the past week, our Sunday, and what we think we can do with the net going forward. And the paper you sent us originally, they used a deep convolution net, but they used contact maps, and we're using a different kind of representation. So I was suggesting that we could just read their paper and use their structure, but they're doing a 2D net instead of a 3D net because it's a contact map.
I'm not super familiar with like the inner workings of context map, but I guess I can read up on it.
Oh yeah, that's their images that they're feeding in. The contact map is just if you have n atoms in a protein, it's an n by n matrix, so the pairwise distances between all of the atoms. Often, when you have that representation, you can actually use that to rescale the three-dimensional structure of the protein because you know the distances of all atoms in the protein.
Is there like an encoding for angles between, like for the bonds and all that, or is that like?
You don't need that because it's all. So if you like define something in 3D space, you can still capture all the information in 2D if you just have all of the distances between the atoms. That's all the information you need, is just the distances. I don't know if you need to encode the angles as well. Because you could just set 1 as your reference. You could set the first, like the 0, 0 as your reference, and then everything will just be based off that.
I guess so, yeah.
Yeah. Anyway, so I don't suspect we're going to be rushing doing another Sunday paper marathon anytime soon, unless Yet throws us another conference. But I did want to think about some of the other projects that we talked about in the past while we kind of take time to think about this one, because I really would like there to be an elegant solution to this, but I don't suspect that it'll come quickly. So if we look, I actually added some things in the README for protein nets. So just some paper ideas, right? This was the first one. It was annotating whether or not proteins were functional. The second one is, once we get the GAN working, which we don't have it working, is to introduce a multi-classification problem where you can assign them to different classes. Like you might have proteins. All the idea is you train a GAN that's good. You train a GAN to the point where you train a generator and a GAN to the point where it can generate proteins, but then you want it to train proteins that have specific functions. So it can cut RNA, it can bind a ligand, it can act as a channel protein. Of course, these would be larger structures, so I don't know if we would get to this, but it's just another idea. So that's once the generator is finalized. This third one is something that I think would be pretty cool. So we have, right, I think autoencoders are a little easier to work with than GAN, just because the architecture is just working off of a single network instead of two. And I just want to get a little funneling thing in here. So yeah, so this is an autoencoder. So the idea is that you're taking some input X and you're compressing the space that it's allowed to be represented by. So we're taking R5 and we're squishing it down to R2. So you're taking like 5 features, and then in this, what they call latent representation, you can visualize this in 2D space. And then you're trying to build that back up to R5. And the reason why you do that is because you want to just compress out all of the irrelevant features. And if you can bring it back to 2 dimensions, then you have been able to kind of you've been able to encode R5 into something meaningful in R2 that can be reconstructed into the decoder, that when you decode it. And the way this works is that you feed in an image and you can encode it and then decode it, and then you take the difference between the decoded image and the original image, and that's your loss, which is pretty cool. There's something called noisy autoencoders, which is when you take a picture, you add noise, you send it through the decoder, you compare the generated or decoded image to the non-noisy image, and you effectively try to remove the noise that you added in. So where I'm going with this is, if we had proteins, right? We have our proteins on the far left. We have native structures right now, and that's what we've been using for the GAN. Those are the functional proteins, the real proteins. And you move their atoms a little bit, or you do something to the protein to kind of mess up its shape just slightly. and you send it through the autoencoder, and you compare the predicted to the original non-messed up structure, you could try to see how you could kind of denoise that noisy protein by seeing if the autoencoder can move the atoms back to their native state. And you do this by, and my idea was to iteratively increase the degree at which you move atoms in a structure to see how far an autoencoder can be trained to kind of reconstruct proteins. That's just a theory. So the idea is you train it on something small, you'd save the weights, and then you'd use those weights as like you set that as the initial weights for the next round of training, and you train it when you move the protein slightly more, and you keep doing this, and you could track the loss to see, okay, so at what point does the loss stop decreasing, and it actually just goes up because the proteins have been shifted out. The atoms in each protein has been moved so much that you can't reconstruct it accurately. Yes.
Do you think the denoising process is going to be like the same, like constant between different proteins? Like if we perturb different proteins, it's likely that like the operation we need to move them back into their native structure is going to be different.
It will be different per protein, right?
But
That's
like, then you just want to like train it on individual proteins. Is that right?
No, different proteins. That's a trick.
Well, I know, but like, I don't know. I guess I'm skeptical about like the ability to train like a generalizable denoiser for something.
Yeah. So what if you didn't move all of the atoms? What if you moved a subset of the atoms? So maybe you could learn. It could learn. What it would do is it would if you move a subset of the atoms, like let's say you have like 50 atoms in a protein, you move like the last 10, it can learn from the first 40 and then apply what it should look like on the last 10 when it's kind of in this encoding and decoding phase.
What do you think is like the utility of being able to do something like that? Like for something outside of like just like proof of concept, you know, like
utility. So the reason why I think this is really cool is because what you want to do when you're trying to find optimal protein structures is you want to basically you have an amino acid, you suppose that there's a structure, and then you try to alter that structure until the energy decreases, right? So if you can kind of treat this as a way of if you get in where the energy is decreasing, and that function isn't differentiable, so you can't do gradient descent to find the optimal you can't do that to find the local minimum of the energy. But what you can what I'm supposing with this is that you could train protein structures that are close to being native to its native state. So so if you were able to predict a structure and a structure has already low energy, you're going to ask, okay, does it have lower energy, or what's the structure that has lower energy than what we what's a structure that has lower energy than what we predicted?
Yeah, I think I understand. It's just like it's a difficult problem.
Yeah, it is a difficult. It's the protein folding problem. I love it so much. Yeah, cool. It's just an idea.
I have a question about the current protein representation. So is there any way to make it smaller? Like,
yeah, there is.
There is? Okay.
Yeah, you can do you can decrease the resolution by just you could decrease the resolution by basically not. I made each block an angstrom cube, but if you look at like the radius of carbon atom, if you get the radius, it won't tell me much because you have to look at the bond radius of carbon atom bond length. Basically, if you decrease the resolution, you don't limit. Like the idea for me is to limit an atom per angstrom cube, but you can kind of put multiple angstrom. You could put multiple cubes in. You can put multiple atoms in the same cube, and that representation, you would just get more features in. You'd get more features per object, but you wouldn't have such a big cube, right?
Oh, so will the data, like the size of it, decrease?
Yeah, it would by a lot, actually.
Oh, okay.
Like
then,
think, right? Look, okay, I brought this up. This is a bond length, right? So it's about an angstrom, and this is why I chose an angstrom cube. And the reason why this is important is because if I made each cube 2 angstroms, right, then our maximum or whatever architecture we have, the volume would effectively
by
8. Yeah, but in each object, you'd have the possibility of having 2 more. You double the features. So really, you gain 8. You gain 4. Sorry, you gain a loss of 4.
Okay, then can we? I just want to see if the game works or not. So can we just kind of like have the infinite angstrom protein?
You want to have?
Yeah.
You want to
so
just go to the other case where
so
you
like,
just
like infinite angstrom, like just like this one dimensional feature, I guess.
okay. You want to do that? You want to do that instead?
Oh, I just want to see if it works. So like,
Okay.
just the simplest case, you know.
Yeah. So the simplest case is when you have all of the atoms and you store their occupancy values relative to the center.
Oh,
right.
What do you think will be the size?
It would just be a vector. It would be if we have n atoms and we have 3 features, it would be 3n long.
Next question. Can you still reconstruct a protein?
With that?
Yeah.
So if you that's the difficult part because, right, where is it? I want to go to the paper. Right, so I don't know if you can reconstruct a protein from this. And I don't think you can. Because we have energy. What we can do is we can just store pairwise distances. I don't know how you do that in a 3D structure though.
Wait, then does the generator have any point? Like
what do you mean?
Basically, it will just generate. It will just kind of like try to make fake protein energies, right? But we can connect that.
The generator can learn. The idea is the generator can learn from using convolution to get like the positional information isn't stored in the features. It's stored in the protein, the encoding.
Okay.
That's the idea. You store the positional information in the encoding.
So the encoding is important.
Yeah, it's kind of how you retain position, and then yeah.
Okay, but you can't reconstruct the proteins from the representation.
Which representation?
Or like the encoding.
The encoding we have, you can, yes.
You can? Okay, so if the generator generates a protein structure or encoding, you can get like a real protein out of that?
Yeah, more or less.
Okay. So to what extent? Like if we make the angstrom like 2000 or something,
I don't think so. The whole point is because you're able to restrict a protein. You're able to restrict an atom to a local 1 by 1 by 1 angstrom cube. That's the whole point.
Oh, okay.
Right.
Okay. Well, for now, I won't care about reconstruction. I just want to know if the GAN does anything. So
Okay.
yeah.
I'll think about that. But yeah, if the autoencoder or this GAN stuff doesn't pique much interest, we can always look to another project for this term. We're only in week 4, so we have a lot of other things we could do. There's a lot of other implementations with GANs, and we have the architecture built, so it's just about feeding the right data, right? So if we want to go away from proteins and then do something else, it's fine by me.
Mm.
Yeah,
Yeah.
have to think about what that would be. But
Yeah, just, something you find interesting. I don't know. Like, I don't know. Have they used GANs to generate fake text, or would you use something else?
Oh, if it's an
Talking about,
image
like-
or text.
like NLP
Sorry?
stuff, is that what you're talking about?
Yeah.
That's like one area that I'm not very familiar with at all. So
Yeah, you I think if you want to generate text, you should use GPT-2 or something.
Yeah,
I know, like
I don't know what that is.
STMs are.
It was just a bad
that.
idea, I guess.
I know, like-
I had a random idea. So, you know how, Osamu, Professor Cam was talking to us about how he created that really strong model to predict the next data point in heart rate
That-
signal?
Yeah.
I wonder if you can combine that with a GAN so that when you start predicting on when you start like shifting your window so that you're predicting on your predictions, it can classify as to whether it's going too far out of bounds or not. Basically, what Professor Kim was doing in a project is he was taking ECG signals, electrocardiogram, it's what the heart looks like.
Echocardiogram, I think.
Yeah, that. Right, so he was taking this wave, something like this.
Electrocardiogram, I guess.
Yeah, so I don't know if it was like this, but it's still a waveform. And basically he was asking, okay, if we have like from here, you see my mouse, from here to here, and we have this region, can we predict the next point? So if this was in like 100, if this was in like 60 hertz, you're trying to predict the 1/60th millisecond after that window, or whatever your window size is. That's a bad explanation. Basically, if you have 50 points in a time series data, can you predict the 51st point? And when you do that, only using non-predicted values or not values that you haven't predicted, you do very well. But if you try to predict on your prediction, so you just start sliding that window to the right, you tend to like go far away from the actual data because the losses just accumulate. And my thought was, okay, so why don't we train a GAN? We use the GAN architecture to kind of learn what these waves should look like, right? And then you can tie it in somehow with the idea that you're predicting on prediction. So maybe that, the generator could be backed by, I don't know how you'd mix them in, but it's just an idea. Because the idea is that you're predicting on predictions. It should go out of bounds. It should be real or fake, right?
So is this sort of like a time series forecasting type
Yeah,
of?
it would be time series forecasting. And Professor Kim said that it is a very difficult, it's a low-hanging fruit. That's what he said. I think he said it in a meeting. He said it's a problem that people, it's exactly what that is. It's time series forecasting, and you're using a GAN to basically classify at each given point whether or not you're going too far out.
What do you mean by classify? Like DSTM or something predicts the point, right? What do you mean by going too far out?
Remember how he said that losses tend to accumulate and you tend to diverge from your actual signal?
Oh, if you keep using the predicted data point.
Yeah. Then you just use the window, that you use the window of what you predicted, and your most recent prediction, or maybe 10 points of your recent prediction, and that could tell you if you're going too far out. And then maybe you use that information to do a reprediction, or you use that information to adjust weights by what it should be, because the discriminator can tell you that you're out. The generator can tell you what it should look like.
Oh, so you mean like the generator generates the next point and the discriminator discriminates or something like that?
I guess so, but it would be more of an LSTM architecture because that's what Professor Kim said worked very well. I'm going to share my whiteboard.
It sounds similar to like the stock market thing that you're working on.
That wasn't, yeah, but that wasn't GAN. We didn't use a GAN for that. I don't know if
I
this
know,
is actually,
but like,
it sounds very, I think this could be applied to a lot of different time series forecasting. But the idea is that you have like some wave, and what Dr. Kim explored is, okay, so if you take a region like this, you put it into an LSTM. Basically, the idea is how well can you predict this point? So if you have 50 here, you're trying to predict the 51st point that's yellow. And what I'm supposing is that you have this LSTM architecture, but as you move this to the, as you move this sliding window, that's bad. I want to get this color. As you move this sliding window to the right, one expects your prediction to kind of just like the losses to accumulate. Really bad. So maybe you start to go this way. Oh God. You start to go this way, but then you just like dive out or something like that. Like red is what is, green is what you predicted because the losses just diverge or accumulate. So as you slide the blue thing to the right, you use the discriminator in the GAN to evaluate a window. So let's say like blue moves here, right? Used to evaluate a window, and that window will tell you, okay, this is not what it's supposed to be, and maybe it can, I don't know, maybe it can use the generator. That's I don't know if that's
personally
feasible.
Since I spent like Sunday kind of like doing the protein net thing, I would like to continue it and hopefully get some money. But for this one,
I understand.
For this one, I think like I don't think
It's
you
just
need
an
a
idea.
discriminator because basically you already know what the data looks like, so you can just compare it with the data.
Well, the idea is that you wouldn't have this red, like this red part is like what the signal should look like, but you wouldn't have it.
Okay, then what will be the usage of that? Because like even if you predict something, the discriminator will just say it's good or bad, right? So if it's bad, just kind of like, I guess, to tell the user that it's bad or something.
Or you can, or when you know it's bad, you can try to adjust to make it good. You could perform some adjustment.
It seems like to me that you could just build all of this into the same learning step. Like you're trying to generate data that is good, not that like, I don't know. It seems like we're doing, like you're trying to make this implementation work for a GAN, even though that might not be the
the best solution.
To use.
Okay, I understand. So never mind.
Not to shit on your idea or anything.
It's fine. No, I have a lot of ideas, and then some of them turn out to be really pretty good, but then some of them are just not. So you would not believe the bad ideas I come up with.
There's a lab that I really like most of the work they put out. I was thinking about looking at some of their papers and trying to do something with one of those, but
sure. Yeah. Cool.
Yeah, I can maybe I'll talk about it next meeting if I find something. But
Yeah, if you do, I'll. If you don't, let me know and I can try to scrap something together. But we'll see about getting some results. I'll look into downsizing resolution.
Oh,
Maybe
thank you.
maybe it'd be good to kind of integrate our encoding with a contact map. I don't know how you'd use both of them as features, because you can't, you wouldn't simultaneously be able to generate two images and then discriminate. Or maybe you could. Could you simultaneously generate, like if you had two generators and one discriminator, and you use information from both of them? Is that a thing?
I think like the way to do it will be to encode both the contact map and like the other thing into like one feature or like one
Okay.
data set.
yeah, you can put it all into the same.
Yeah.
You can't have two generators and one discriminator.
I think you
Like-
could. I just like.
Well, you can, but like how will you train that?
I mean, you could.
I guess it's just
You
like
could do two updates per.
Yeah.
Two generator updates per discriminator update. I guess that's what.
Yeah, but it's like going for a complicated solution before trying out a simple one.
Yeah, and then like if one generator doesn't have the same like desired outcome,
Yeah, I guess you're right.
like maybe you have like competing information that you're feeding your discriminator, and then like it doesn't train well or something. I don't know.
Yeah, maybe. Oh,
Okay.
now that I think about it, if you just make it like infinite angstrom or like 2000 angstrom, will the GAN just learn like what atoms should compose a protein?
I think so.
Oh, okay, that'll
then-
be interesting.
And then it would also try to learn, because like the other feature is the occupancy, so it would learn how far each atom is from the center, roughly.
Oh, okay. I think that's a simple enough thing to start out with.
Yeah, but
Yeah.
the problem is the equation I'm using is scaled to angstroms, right? So if I make them, if they're so far from the center, then it'll go to 0. So you won't really get that much information.
Wait, so all the values are gonna be 0.
All the occupancy values would be 0, yeah, except for like the angstroms closest to the center.
Oh, then I can just remove the occupancy values.
Okay, so you
Alright.
want to learn positional atom types?
Yeah, just atoms. At least for now, like
There's
you
just n
understand.
atoms. There will be n alpha carbons and roughly n beta carbons.
Yeah, it's kind of like I don't know. Like I understand it's underwhelming, but like you need to start with MNIST before you can.
Yeah, we
keep it safe.
could try to just use a contact map, because that's what the paper used, and
Oh yeah,
it might be a
let's say
good
that.
thing. Yeah, it might be a good thing to just reproduce their work.
Oh,
Yeah,
that's fair. Yeah.
yeah,
Oh, did they use again too?
yeah.
Oh, okay. Yeah, let's just do
where
that.
That's where we're coming from this.
Oh, okay. Yeah.
The paper. Cool. Yeah. Well, if you guys have any suggestions, just let me know. They're kind of just trying to figure out what I'm doing week by week here. So cool. All right. Yeah, that's it for me. If you have any questions, you
I
can
have
stick
a
around,
question actually.
Sure.
So about the previous problem where your professor mentioned using ECG signals, like what's the significance of that problem? Let's say if we predicted the 51st signal position correctly, like
I can answer that question. So basically, when you're in a hospital or something, the most important thing for doctors is to understand the state of the patient and understand how they're gonna be in the future. So if you can predict like the next point and like I don't know, point in like 200 seconds or so in the future, then it'll be really valuable because they will know that, oh, he's gonna have a heart attack in like 200 seconds. We should do something. So
that's
yeah.
that's cool.
Yeah.
That's a good explanation.
Like an arrhythmia or something.
Yeah.
Yeah.
So that's why I think it'd be good. I don't know how you fix that, because is there a way to feed back the fact you could tell the network, hey, you're going out of range. do something. Don't. Or this isn't a signal. This or if the model knows that it's predicting a signal that it doesn't look like anything it's seen in the past, then it can be more. It can maybe change some parameters in a way that kind of, I don't know, moves it back toward equilibrium. It's like the ball on the hill example. Like if you have a ball, if you have like a parabola, you have a ball like on the right side, it's gonna drift and then it can go back down. So it has momentum until it goes back to the center. And the idea is to basically tell the model which side it's on. So like that's analogous to like being above or below the signal you're trying to predict. So if you could tell the model it's below, maybe to adjust parameters to go back up, and then if it goes above, it goes back down to the signal. I don't know if that analogy makes any sense, but
I think it's an interesting approach. I just doubt it will work.
nice.
like I think, I don't know. I think like just doing like simple gradient descent will make it look pretty good, but yeah, it'll be interesting to try it out though.
I don't know if it would be gradient descent. It would be, yeah, I guess it would be, but it wouldn't be on weights. It would be on the predictions. You'd want the descent. I guess it would be.
And like this is all assuming that the other model that predicts up and down is accurate.
Yeah.
But like
predicts that it's wrong. A, B, that it's up.
Yeah, but like we don't, the model that predicts the next value, that's unstable, right? So what makes like the prediction up and down stable? Yeah, I think it'll just make it more unstable. That's my guess.
That's just like having enough sample data.
Oh yeah, like with enough data, anything's possible.
Okay, cool. All right. Thank you guys. Good questions.
Are we gonna talk any more about like logistics stuff for the conference or anything like that? Not that like you're responsible for all of it.
Should I have answers?
No, I just
I'm kind of hoping that Yit's gonna do it this year, and then like we'll figure it out next year. So if you have any questions, ask him.
Okay.
Yeah. Logistics. It's happening the end of May. I know. we need to
find these conferences to do.
Sorry?
How does he find like all the conferences to apply for?
Oh, there's probably some website, but the conference we're talking about is going to be the one we're hosting.
Oh, okay.
Yeah.
Okay.
So how do you find that one? Dude, he made it.
How many submissions are there for our conference?
Last time I checked, there were 0. So we have to really encourage. I think if we encourage people from sparse labs, I have another lab I'm a part of at Drexel.
Yeah, I'll submit.
Oh,
some.
Thanks. well, Jeff.
Yeah,
I'll
reach out to some I'll reach out to some professors because I know some of them who are doing like research with some students, like some grad students or something.
Yeah, we can like ask STAR students to do stuff maybe.
Yeah, there were 2 other machine learning projects that I could try to. I think they were trying to do breast cancer detection. So it was cool. And then, yeah, I have some other coworkers at my other lab at the Children's Hospital that I could ask, but I don't know if they submit. So we will figure it out. Cool, good question, because we want to get people to submit things, and I'll probably have someone on that paper do a presentation on this project that we just did, because why not? And then I can submit a work I did, I don't know, a while ago. Cool.
Sounds good.
Right. Any more questions?
No, I'm
okay.
good.
Okay,
Yeah,
cool.
I'm fine.
Sweet. All right. Thank you guys for tuning in. I'll see you guys next week.
See ya.
See ya.